Hello everyone, and sorry if the slides are a bit small, but well, we had technical issues and this is the best we managed to do. So before we start, let's say a couple of words about me. In the open source world, I'm mostly known because of my work on PyPy, which is fast Python interpreter with a JIT compiler. I've been doing it for more than 10 years now. I'm also the author of a couple of other projects and modules like PDB++, VMProf, CarpenPy, and etc. All these things have in common that are written using TDD development, test-driven, which means that they are all covered by a lot of tests, and I think they are well written, and so I'm trying, in this talk, I'm trying to give some insight of what test-driven development means and how to apply it in a more effective way during your work. What about you? I expect the audience to be either composed by either novice programmers, people who are approaching programming and they know a bit, but they never did any proper testing, or experienced programmer which know how to program, but they really never tried to write proper tests. So I'm trying to give some information to both, basically. And the talk is divided in two parts. The first is about a general principle about test-driven development, what it means, what's the goal. And then I want to show some real-life code patterns which I have used in multiple times in various projects, like the projects I showed you before. Because in my experience, every time I see a talk about test-driven development, they talk a lot about general principle and etc., like my first part, but then it's hard to understand what actually means without having a concrete example. So I'm trying to show how to actually use the suggestion I'm giving in the first part. So let's start with obvious. So what is the goal of testing? The goal of writing tests for your code is to make sure that your code works. Do you agree with this sentence? Of course, it's wrong. The actual goal of testing in test-driven development is not to make sure that the code works, is to make sure that it doesn't break eventually. Because writing a code which seems to work at the beginning, it's kind of easy. It's what everybody does when you start and to learn to program. You want to do something, you have the feature to implement, you write the code, then you start the program, you see that the program more or less does what you wanted, and you're happy. And sometimes it's checking that the thing works requires a bit of steps, like you have to log in to a web page, click a couple of buttons, checks that the output it's what you expect, and etc. So this is what you usually do when you do a manual testing. Of course, at some point your feature doesn't work, you repeat until it works, and you're happy. Then later you want to implement another feature. So you do the same, you modify the code, you do click, click, click. You see that the new feature works, you are happy. But in the meantime, you broke the earlier feature, and you didn't check it again. So maybe you commit the code, you deploy, and you have a bug. The point of using automated tests is that once you write the test, you do basically the same thing as you do in the manual testing. You check that the output you get is what you expect, but you write a program to do it. So the next time you can just run it and make sure that your feature still works. So in this case, you write the code for feature A, you write the test, you run it until it's fixed. Then when you write the code for feature B, the new test works, good. But then when you run the entire test suite, you see immediately that the test A no longer works and it fails. So you know that you have a code, and so you can fix it before committing, before deploying. So this is basically the idea. Of course, all of this is a nice theory, but there is a missing piece in the puzzle, which is, well, we need to write a test, because manual testing is easy. You just use your application and you check with your eyes. What is a test? Actually, a test is nothing more than just a program. It's a program which executes your code, your library, your web application, whatever it is, and it programmatically checks that the output is what you expect. If you have to write everything by hand, then it quickly becomes annoying and time-consuming. That's why we have a lot of frameworks which help to write tests and to run them. Like you can have your test suite with a lot of tests and run just one, the one you are using, and etc. There are many frameworks like unit test, which is included with the standard library, unit test 2, nose. Here I'm showing example using PyTest, which is the tool I'm using, and I personally suggest because it's the one I like the most. But any framework is better than no framework, so, and no test even. So what we said so far is that the goal is to make sure that your code does not break, and we have a way of saying, especially in PyPy, is that if you have a feature which is not tested, it's the same as having it broken. I mean, maybe it's not broken right now, but eventually it will break. As soon as you have a code base which is millions of lines of code or even less, it's very easy to break things because it's impossible to understand all the possible code paths and dependencies and etc. So you should write a test to ensure that in the future your code will not break. This is a general theory about testing, but test-driven means something very specific, which means that the test comes first. So in general, the principle is that writing new code without having a failing test is forbidden. You should never commit code which has not a test which fails if this code is commented out, basically. And if you want to apply it even deeper, you write the test before writing the code. So basically the idea is I write the test, maybe because I have a bug report. One user says that if I do this, and that, the program crashes. So I do the test which simulates the same. I see the crash, then I can write the code and check that the test now passes. By doing this, I'm ensuring that the test is actually checking the code I'm writing. Else it happens, and it happened to me. All of these suggestions, I say them because I was beaten by them, by these mistakes. I write the code, then I write the test, but the test is testing another code path because I did a mistake. And then, yes, the test succeeds, but my code is still buggy because I'm not testing it. So you write the test first, you check that it fails, you fix and check that it passes. But this is the idea. Moreover, you must ensure that each test can be run in isolation. So if you run the test alone, it works, and if you run the test with all the other tests in the test suite, it still works. Sometimes I've seen in real life code bases in which if you run all the tests, they pass, but if you run one test in the middle, it starts to break because it depends on some global state which was set by another earlier test. So this is something we should try to avoid as much as possible. The good point of doing this is that it integrates very well with the version control system. For example, every time you write a test and the corresponding fix, you do a commit. So in the same commit, you see what is the code and what the code is supposed to do. And when in the future you will see, okay, why did I write these 2 lines of code? What's it's doing? By looking at the commit, you see what is the test, and you can understand why they were written. Or you can also try, for example, to just comment out the line of code which you are not sure what they do and see which test breaks. By doing this, then it's very easy to refactor your code. I've seen code bases in which you have tens of hundreds of lines of code which are never executed, but people maintain them because, well, because they are scared to kill them, because they have no idea what's happening. If your coverage, if your test coverage is high, then you can just kill the line of code, and if all the tests pass, you can be sure that your application is still working. If you delete the code, the tests are passing, and then the application has a bug, well, it means that you are missing a test. So you write a test, and next time you will notice this kind of breakage. Really, I personally think that this is the most powerful feature of having a project with a good test coverage, is that it lets you to refactor things, to restructure, to move code around, to do deep refactoring, and you are confident that you didn't break anything. I mean, in PyPy we do it every time. PyPy is a very complex project. Sometimes you really have to do heavy refactorings, and without all the tests that we have, it would be impossible. You would introduce 10 bugs for every line of code you change. And it happens. I mean, I write a couple of lines of code, and then I test in another piece of code which I could never think about is start to break because it's important and I didn't see, for example. So, in this slide, I'm talking about the properties of a good test. Some of them is something that I just said, like the test should fail before the fix. The test should be deterministic. You should never commit a test which fails every other run because it's flaky, because it depends on external connection, etc. You should really ensure that a test is always passing or always failing. But if you have a test suite that every now and then as a failure, oh, it's fine, and you forget. But then you become used to the fact that your test suite is failing. And this is not good. You should really be worried when you see the tests are red instead of green. And also, while we are at it, yes, we write a test, and the test should be easy to read. You really can think of them as executable documentation. Like, what is this function doing? Well, I read the test and see what is the expected output and what is the expected usage. So if the test is easy to read, I can learn what this function, what this class is doing, what this module is supposed to be used. About readability, and now I'm start to show some example, because so far it's just a lot of talking without any concrete example. Readability is important. I think that the test should really tell a story. Like, I start from here with this prerequisite. I tested this feature, I do these steps, and I check that the output is what I want. And please avoid complex control flow inside the test. If the test is as complex as the code, then you cannot be sure that the test is correct. Maybe you have a bug in the test. And also, if the test fails, then when you have to debug the failure, you have no idea what's happening, because you don't understand either the test or the original code. So this is an example for testing a factorial function. Factorial is very easy. I think it's the easiest function I can think of, apart the identity, maybe. And this is a test which checks, for example, that the factorial of 5 and 7 is computed correctly. What is wrong? What is the bad part about this test? Is that basically here there is a for loop which basically re-implements the same logic as the factorial function itself. You have to read to understand what it's doing. It's multiplying numbers and etc. And then it checks that the function, then the result is correct. But here, really, I'm not testing anything, because I'm sure that I'm not sure, but it's likely that I wrote the same kind of code in the original function. So if there is a bug, there is a bug in both. And actually, this really happened while I was preparing the slides. Well, the test was broken. I didn't write it to be meant to be broken, but I made a mistake, and it was. I don't remember even what was the actual error. So a better way of writing the test is this. Here, I don't have any complex control flow. I know that the factorial of 5 is 120, so I just write the result. And this is much better because, well, it's correct, and well, it's really good. And when you read it, well, it's immediate to see what's happening. But there is still a better way because, yes, okay, factorial of 7 is 5,000 and something. Yes, but maybe I typed it wrongly and the code is buggy, and the test passed, but they have back. A better way of writing the test is doing this. This is clear. I mean, this is really executable documentation. It's the definition of factorial, but written in a way that a computer can check that the result is correct. Of course, this is a very easy example and simple, and everything is fine. But the general principle is that when you read the test, it should be obvious why the result is this instead of that. And then the code, well, can compute it. So far we talked about a test which is easy to read, but then we know we are programmers, so we are by definition very lazy. So a test must also be easy to write, else I'm not going to write it. If I use a good framework and a good infrastructure, then writing new tests for the features is really as easy as checking manually by clicking the buttons and etc. Depending on the application, arriving at the point in which writing the test is easy and fun, it's not straightforward because you have to develop your own infrastructure to write the test. But usually it's a very good idea, and it's something which pays itself in a couple of days or weeks or months at most. But really, in a short period of time, you will see that investing time in writing a proper infrastructure is worth. Of course, the infrastructure is a piece of code as well, so you have to test the infrastructure as well, but too bad. So let's show a concrete example of what I'm saying. I hope that the code is not too small, and you can see also from the back. So this is, well, it's a simplified example, but it's a real-life example of something which we do in PyPy. At some point, we want to execute PyPy, like we have an executable, which implements Python interpreter, and we want to execute snippets of code and see what is the result and what are the log files produced and etc. One way of doing is this. I write my snippet of Python code inside a string. Then I create a temporary directory, I create a temporary file, I execute a sub-process. Here, I execute the sub-process calling PyPy, and the file I just wrote, passing parameters. Here, I have to convert the parameters from a string, because it's a sub-process, to integers and etc. And then I convert the standard output from string back to integers again, and I check that the result is what I expect. This is very bad because I have a lot of logic in this test, and it's not immediate to understand what I'm testing. What I want to check is that PyPy computes the factorial correctly, not that I have a subprocess and the subprocess returns 0 and whatever. A better example, still bad, is to move some of the logic outside. So I have this execute function to which I can pass a snippet of code, and it does all the work in a corner. This is a bit better for two reasons. One is that since I have the execute function, now I can write a test for it, and I know that the execute function works and it calls the subprocess correctly and whatever. And also, as soon as I want to write another test which is similar, I can reuse the execute function. So this is just normal development, a good practice of development. But the best way of doing this kind of thing is really to implement a good infrastructure in which it hides all the complexity in some corner, which is well written and well tested in isolation, and then I can just reuse it as many times as I want. So in PyPy we have something similar to this, in which we have a base class for our tests, which is called PyPy test, which has this magic method run, and the run takes a real Python function. I no longer have a triple quoted string. It's really a Python function which is implemented normally, and takes parameters as Python types. Like it's a 5, it's not a string 5 here, and it does the magic. And the magic in this particular case is implemented in this way. I'm not going into the details, but if you skim over the code, you see that basically we use the inspect module to get the source of the function, the inner function I wrote in the test, as a string, so I can put it in a temporary file, execute the subprocess. I have this boilerplate which converts the arguments from strings to Python types and etc., and return the result. So we started from here to here, and we ended here. And I think it's obvious that writing, once you have developed your PyPy test base class, well, writing new test is very easy. You just write the function and execute it without having to care about all the boilerplate. And also it's much more readable, because when you read the test, well, you just see what is the important thing, not all the boilerplate which is hidden in a corner. And of course, you can write a proper test for this class as well. As I said, this is a real-world example, and I have used this kind of approach many times. So here, I will put the slides online later, and you can find links to the project which use this pattern. For example, this is the link to the PyPy source code, which use for doing more stuff, and it's more complex than this, of course. And you see that we have this model.py, which contains all the infrastructure, and we also have a test for the infrastructure, as I said. Or CapMPy is a library for reading and writing Cap and Proto streams, which I wrote, something completely unrelated. But I also use this kind of pattern, and by clicking on this link, you can see how it works. Another useful pattern in testing, and here I'm talking about something completely different, and I'm no longer talking about compilers and text files and whatever, is something which is useful, especially when you have to develop a GUI application or a web application or everything which have to interact with the user. A very nice property about the example I'm showing is that it's used to make your code easier to test, but it also leads to a better design overall of the application. So you really get two nice features at once. So what I did at some point when writing these slides, I really typed on Google tutorial for Kinter, which is the library, a GUI library, which is distributed with CPython, and I found this link, a random link, and I tried what it is. And I cannot show you the demo because I don't have my computer, which didn't work. But this is an example of a very simple calculator. You really see a text box, and you can type numbers, and you can add them or subtract, nothing more. But when I looked at the code, I saw that it was really badly written. Because, for example, you see that here we have a class in which we have some logic which is for displaying the GUI, like we have this label, a button, and things like this, and some code which is really the logic, like if I click on the button add, I need to do an addition. Oops. And if I click the reset, I need to reset the total to 0, and etc. This is really the kind of code that you write when you are a beginner, and you don't decouple the components. So you have the business logic somewhere, the interface logic, but you mix them together because it's easier to write. But then it's really hard to test, because when you want to test such a calculator, what do? You start the GUI application and have the mouse moving around, clicking the buttons and checking what is the output. It's very hard. So the proper way of writing and testing this kind of application is really to decouple the two parts and having one part which only implements the logic without any GUI, and then having the GUI which calls methods on it. So in this particular case, we have this very simple calculator class which does only the thing you need and nothing more. So in this case, we have a state, which is the total value computed so far. You can add values to it, subtract values, reset, and that's it. But then and then you have the GUI, which is as complex as before, but instead of having, we started from here, in which you do the addition and the subtraction in line, to here, where you delegate the logic to the calculator class. And then it becomes straightforward to test the logic, because now I can write a class which has no GUI at all, and I can just write a test. I can check that whenever I call add, I really add the things, and when I call subtract, I'm subtracting them, and reset, well, guess what it does. And I think, again, this is a very simple example, so maybe you cannot appreciate the real advantage of doing it. But when you start to have a really complex application in which the logic is much more complex than this calculator, really the ability of testing each component in isolation without having to depend on all the other components, it really means that your application is much easier to write, test, to read, and to maintain. Finally, if I have time, how much time do I have still? 5 minutes? Perfect. This is the another suggestion I want to show you, and it's one about notation. I originally learned about this way of thinking about programs by reading this book years ago, and by the way, I recommend this book to everyone. It's a bit old, but the things which are written inside are general principles which you can apply also to modern programming. And basically, the thing about notation is that sometimes if you have something which is complex and it's hard to read or to understand and etc., if you write it using a new notation, then it becomes much simpler to read, to write, and to check, basically. So this is another real-life example from PyPy. At some point, we wanted to check that the code generated by the JIT was what we expected. So we gave it, for the optimizer, a list of operation in input, and we checked the list of operation in output, what was expected. But how do you represent the operation? We started by doing this. So each operation was a class, an instance of a class, with a name, with some attributes, and etc. And then we checked the result using the same style. But you can see that if you start to have many operations, it quickly becomes hard to read and to understand what's going on. And then at some point, we decided we no longer felt like to write manually all this stuff, so we wrote a small parser which converts these things here into this kind of, into this. And now, of course, here you don't know what is a guard class and etc. because it's something which is PyPy specific, but I think it's clear that reading these 3 lines of code, once you understand what is this mini language, it's much easier than reading this. And also it's much easier to write. And then when you have to write new tests, it's more fun to write them instead of having to type all the stuff. And so basically that's it, I think. I hope I showed you some interesting concepts, and if you have questions.
I'm sorry, but we are running out of time, so we have to stop here. But we still have some time to a few questions, like 5 minutes or so. Don't be shy.
Okay. You said that the test should be able to run alone, but what if the test depends on some certain state of the overall program? What's the best approach?
Yes. It depends which kind of test we are talking about, because if you have a unit test, then the unit test should not depend on the external state, else it's not unit. If it's an integration test, yes, then you might have to depend on the external state of the system. But what I usually do in this case is to make sure that the test itself is bringing up the system in the state which it expects. And also that if sometimes the state is expensive to set up, like you have a database and you want to check many different functions against the same database, and it's not feasible to recreate database from scratch every time. So what I do is to basically roll back everything at the end of the test to make sure that either if the test succeeds or fails, the state of the database is consistent, and the next test can start from a known state, independently from the success or failure of the previous one. I hope I answered your question.
What you prefer to test? Class methods or some part of the code specific, or what you write first for the test? Cioè, method and then the whole class, the behavior?
I think it depends on the practical case, but in general I don't know what it means to test a class. You test the methods on the class usually, so.
In an object-oriented idea, a behavior of some relationship between classes, how they work together.
Yes, but at some point the logic is implemented inside the method, so basically you will have one test which tests what happens when I call this particular method. Sometimes I prefer to write tests by feature, not by method. I want a test which checks that the two things are compares equal, even if they are two different classes. So maybe I write both directions in the same test because I like to group them together. I don't know, but it's a bit hard to give a general principle, I would say.
Hi. Is there any way to categorize tests? I mean, if I want to categorize all unit tests, all integration tests, in such a way that I can run just a bunch of them because I'm developing such feature and I want just to test them, that feature, instead of the whole code.
Yeah. Yes, this depends on the tool and framework you use for testing. In the case of PyTest, you have several ways of doing it. The easiest is to split the test in different directories, like one directory for module. Then you split them into different files, so you can run either one directory or one file. You can run individual tests inside a file by giving the name of the test, or you can group them into classes, so you can run all the tests inside a class. And with PyTest, you can also mark them. You can give additional flags to each test and say, run all the tests which are marked as GUI. Or run all the tests except the one which are marked as slow. I mean, you can do things like this.
So that's it. If you want to change room, this is time to do that.